I remember that because of the way we arranged our components, replicating the components, we had two problems. One, we had more pins than we needed. Second, the joints between the cylinder and the piston, between the cylinder and the piston, between the piston and the connecting rod, and then between the connecting rod and the crank, none of those copied. So if we really wanted to build an inline engine from this, we would now have no choice but to start manually applying those joints again. There's a better way, and that is you can solve the problem. The solution is to repackage the components and look at the browser listing. So what we have done here is that we repackage the components this way. We have a single component called cylinder assembly. In the cylinder assembly, we have the connecting rod, the crank, cylinder, and full piston. In this full piston, we have the piston itself and the pin, both of them as components inside a bigger object called the full piston. And that full piston itself is now added to cylinder, crank, and connecting rod to make the cylinder assembly. The only thing not in that list is the end one. With this kind of arrangement, it is neater because that cylinder assembly, all the joints between its members are contained inside the cylinder assembly because the cylinder assembly itself contains the control rod and the crank. So the connection between any pair is also part of, instead of being owned by the superior overriding parent component, it is right inside the cylinder. So if you make a copy of this cylinder now, it's going to carry the joints, and then the piston too will carry the piston and the pin as well as the joints inside them. So that is one way. So it is, these are the solution. So a rearranging or a repackaging of your components this way can actually solve that problem. So because of that, if we did that same replication again, this is what we get. We get a situation now where the joints are carried along and there is no problem with replicating the piston pin unnecessarily because there is no double selection of the piston pin again. So that is how a repackaged component with the new browser listing, copy now includes full joints as they are included in the single component being replicated. That's how you get out of this problem. So you have to plan all these things together when you are planning to do your component design. So the last thing we will do in today's class is that we are going to assemble an inline engine. I chose an 8-cylinder engine. So we have an 8-cylinder engine with a firing order of 1, 3, 7, 8, 5, 2, 4, 5. That's not correct. It can't be 5, 2, 4. I think it's 5, 6, 2, 4, 5. So there's an error there. You cannot have a cylinder being repeated. Okay, so let me go back again. So the firing order we have chosen is 1, 3, 7, 8, 6, 2, 4, 5. We start from the repackaged single engine. So we are now starting not from the original single engine, but from the repackaged single engine. In this case, there are only two components. The components are the end rotor, which will actually be a stator eventually, and then the single cylinder assembly, which contains every other thing. And inside every other thing, we have the crank piece, the connecting rod, the full piston, which is now a component of components, whose components are now piston and pin. Rather than the full piston being containing only the pin, it contains the piston itself and the pin as equal components under it. It's easier that way, and then the cylinder. So if we are going to replicate anything, it is this single cylinder assembly we will replicate, and it will carry all the joints that are necessary with it. Because we only need, whatever kind of cylinder we have, whether it is 4-cylinder, 6-cylinder, or more, we only need one end rotor. So this is all that will be replicated with its joints. And this, when we finish, this is how the crank shaft will look like. Of course, if I showed you this crankshaft at the beginning and say, okay, look, do this crankshaft, and then check what firing order is. It will be difficult for you to see. It looks really, really, really complicated by a drawing, but you will be surprised to see how easy this is when we do it. The joint for the single cylinder will be the joints for single cylinder will copy because it is now inside, they are now inside the component rather than a parent component. So we can do pattern replication, grounding information, implementing rotations, joining each cylinder to neighboring rigidly, and resulting. That's what we do. All those things that will now give us the crankshaft that we have here. So we are now talking of theory and skills. You will see that when we talk of the firing order, that's a very deep theory, because you really need to know how a four-stroke engine works and what that firing order really implies. So you cannot just be a very good draftsman and then know what to do. You have to understand the thermodynamics and the theory of the firing order. I will introduce a little of that in this class. Now you can read more on it, because it's peripheral to our course, but it is good for you to pick some knowledge along the way on other things that you may not immediately need, because that is your duty as an engineer, be knowledgeable about what's happening in other areas. So if you come with theory alone, it will be difficult to retain the skills to implement the solution. You cannot learn theory alone, because if you learn theory alone, you won't have any skills. If you learn skills alone, you lack the theory to be able to actually advance in those skills. With skills alone, you cannot gain understanding required to make the product. Combining both helps you to high-level performance. You need skills to contain the theory, and you need theory to advance the skills. So just notice that you need to always look at these two. And Nigeria thinks theory is nothing. And all the people that are practical, they can't do nothing. They can only become cobblers and copycats of other people's products at best, and they will not even copy it well. But let us go back to the issue here, the firing order. In a four-stroke engine, there are 4 traversals of the piston in the reciprocating motions. Goes forward, backward, 4 traversals. A single repeat completes a full crank rotation. Go forward and backwards, or backwards and forwards, will give you 360 degrees of a full crank rotation. 2 repeats or 4 traversals will give you 2 full crank rotations. So 360 degrees times 2 is 720 degrees of angular traversal. If this is shared by 8 cylinders, that shows that each cylinder will be fired in 720 over 8 degrees. So every 90 degrees, 1 cylinder is fired. So the only thing is that how do you now orient the cylinders to each other so that you have a predetermined firing order? Now, we have said we want a firing order of 1, 3, 7, 8, 6, 2, 4, 5. You can go to Wikipedia and read on firing orders of available engines that are out there. You put 4 cylinders, 6 cylinders, 8 cylinders or bigger, so you can see. And it will be a good practice for you to implement a different firing order than the one that I've implemented here to really show you know what you're doing. So before, we have to use some theory to calculate what we have to turn this firing order into angular rotations. So that's the first thing we have to do. So to do that, it's not very hard. So let us see how we do that. So since the total number of degrees, 4 traversals will give us 2 full rotations. That is 360 times 2, giving us 720 degrees. If this is shared by 8 cylinders, then each is therefore inclined at 720 over 8 to its next firing order, because each one is fired at 90, every 90 degrees. So the next one must be 90 degrees away from the previous one, and so on. The next firing cylinder is determined beforehand, and that is the meaning of the firing order. Okay, let us see now. We have 1, 3, 7, 8, 6, 2, 4, 5. So if we calculate the first one, that is cylinder 1 at angle 0. Then since the angle cylinder 3 must come immediately after, so it will lag it by 90 degrees. Then cylinder 7 will lag cylinder 3 by 90 degrees, making minus 180. Again, just add minus 90 to each one. You have 180, 270, 360, 450, 540, all of them negative. Those are the angular orientations of cylinders 1, 3, 7, 8, 6, 2, 4, 5. If you have that, and you know that if you going counterclockwise at minus 90 is written as going clockwise to 270. Going counter at 180. 180 is 180, whether you go clockwise or the other, you are going to arrive at the same 180. So 180 does not change. Similarly, by the time you get to minus 270 is the same thing as plus 90. Minus 360 is the same thing as angle 0. And minus 450 is the same thing as 270. And minus 540 is the same thing as 180. And minus 630 is the same thing as plus 90 degrees. So that is so the same thing. So 1, 3, 7, 8, 6, 2, 4, 5 have angle 0, 270, 180, 90, 0, 270, 180, 90. But suppose we arrange it, we want to know now, if we look at cylinders 1, 2, 3, 4, 5, 6, we can copy the angles that are here into the cylinders now arranged in order, because our cylinders are physically arranged in order. But in firing order, they are arranged in a completely different way. So I haven't known what angle of cylinder 3, we can put it here. I haven't known the angle of cylinder 4, we can put it here. I haven't known the angle of cylinder 2, we can put it here. So that we can arrange the cylinders in order. So these 3 tables are exactly the same. The first one is showing the actual degrees of firing. The second one is calculating it because you cannot have any degree more than 360. So So that's the thing. So we just reduce them to the primary angle between 0 and 360. And then here we are arranging the cylinders in correct order. So that is how we compute the angles of the firing order. That means that when you have cylinder 1 at 0, you must rotate cylinder 2 through 270 degrees. Then you must rotate cylinder 3 through 270 degrees to 0, 4 through 180, and so on. So that's how you know how the things will fire. So we start where the way we do it. This is also shown now in this link here.